is the 9-2 notes. I filled them in, so again, you can pause as much as you want. I'm going to go very, very quickly with the idea that hopefully you are going to pause at different points and mark your diagrams or try the questions for yourselves before you hear my answers. So we went through, we talked about this a little bit. If a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So right where the radius goes to the point of tangency, this is always going to be a right angle. And we'll get more into the proof of that a little later in the next lesson. Tangents to a circle from a point are congruent. So that means from a common point. So you can see I drew two tangents from this point right here, and the segment from this point to the point of tangency will be the same as this point to the point of tangency. So tangents drawn to a circle from a common point are congruent. This is the converse of that very first theorem. If a line in the plane of a circle is perpendicular to a radius at its outer endpoint, then the line is tangent. All I did was reverse what I had in the first one. This is using some of the similar vocabulary we used before. The polygon is circumscribed about the circle when each side of the polygon is tangent to the circle. So if they say this quadrilateral is circumscribed about the circle, what you then know is that all of these segments are tangent to the circle. And if you look here, these are two segments drawn from a common point, so that would mean these two parts are equal, these two parts are equal, and you can work your way around. The circle is inscribed in the polygon, so again, inscribed doesn't just mean inside, it means it's tangent to the sides. More definitions here. A common tangent, circles can have common tangents. A common internal tangent, I kind of use that green to show the connection of the centers. So a common internal tangent would be here. This red line that I'm drawing is an example of it being tangent to two circles. There's actually two of them. So it's tangent to both the circles and intersects that green segment. So that's a common internal tangent. A common external tangent is going to be tangent to both circles, but it will not go through that segment that would connect the centers. So these two lines are examples of common external tangents. So common tangents would be lines that are tangent to both circles. We can also have circles be tangent. So this example here is circles are externally tangent. They are kind of bumping their outsides. They intersect in exactly one point. Over here, these circles are internally tangent, again, intersecting in one point where one is inside of the other. Over here, what I'd like you to do, first you might want to remember this is a radius. I can tell you, I did write this on the board in class, OT is tangent to the circle R. So I know I should have told you that in the beginning, and in the quizzes and things I will. But OT is, I will tell you, it's going to be given OT is tangent. So because this is a radius and a tangent, you know that's going to be a right angle. So I'm going to encourage you now to try to solve these on your own, to push pause. The other piece I'm going to put in here is a little extra piece. If I call this point A, where this segment meets the circle, in problem 2, I want you to find RT and also see if you can find AT. It's a little bit trickier, but you can do it. So push pause now and see if you can solve these. All right, on this screen I've gone through and solved them. In number 1, everything is in red for number 1. So I labeled OT as 18, OR as 6. This is a right triangle. So I used the Pythagorean theorem. I did not know, see the blues, I don't know that in the first problem. All I know is two sides of a right triangle. I used Pythagorean theorem and I got that RT was 6 root 10. In number 2, everything I did in number 2 is in blue. So I labeled these angles 45. I knew OT was 4 because they told me that. So if OT is 4 and this is 45 degrees, then I also know that OR is 4. because 45, 45, 9 special right triangles. So RT is 4 root 2. Now to get AT, that might seem tricky, but we just found out that this whole thing was 4 root 2. And I know this piece is 4 because OR and RA are both radii. So RA is 4. So AT is going to be that 4 root 2 take off 4. So that was the length of AT. All right, in this one, again, I'm going to encourage you to write this down or look at the notes that you could print offline. I'd like you to try and attempt this yourself. Okay, M, N, and P are collinear, so you can draw a line that connects all 3 of those. And I would like you to try to solve all 6 of these and then come back. Okay, on this screen I have solved them for you. So for PM, well, it said that circle N has a diameter of 16. That must mean it has a radius of 8. So N to P is 8. So P to M, since that's a diameter of circle M, PM would be 4, which is right here. To get PR, I just used segment addition and did 3 plus 12. Number 3, NS. NS is a radius of circle N, therefore it's half of 16, which is 8. To get MQ, I drew that in and see the right triangle. I knew this was a right angle because MP is a radius and PR is a tangent. The intersection of a radius and a tangent is a right angle, so I drew that in. Now I know PQ is 3, MP is 4. I can use Pythagorean theorem. Some of you know it's a special right triangle. So MQ is 5. To get SR, SR is a tangent drawn from R, so it's going to be the same as RP. That is also, they are 2 tangents drawn from a common point, so they are equal. That's why SR is 15. And then for NR, you can see I had NS being a radius. This is a tangent. I drew in my right angle. I don't know the angles here, so don't assume you know that, but I know I have a right triangle with 2 sides. I can use Pythagorean theorem, and so NR is 17. And that concludes the 9-2 notes. Check online for the homework.